Hi, welcome all to the online classes. I'm Mukesh Bhardwaj, going to deliver a topic, rectifiers. We had started the rectifiers in the last lecture and we had completed the half wave rectifier and the full wave rectifier. And in the full wave rectifier, there are two full wave rectifier. One is the center tap full wave rectifier and the another is bridge wave rectifier. So we had completed the center tap rectifier, that is full wave rectifier. Now I'm going to start with bridge rectifier. So just wait a minute. Rectifier, the definition of rectifier we had completed, the theory related to that, and the types of rectifier we had discussed. Half wave rectifier, the operation of half wave rectifier with the capacitor as a filter. Now we have already discussed about the characteristic of half wave rectifier, that is ripple factors, peak inverse voltage, rectifier efficiency, root mean square value of load current, root mean square value of output load voltage, form factor, advantages of full wave rectifier and disadvantages of full wave rectifier we had discussed. Now half wave rectifier with the filter circuit, we had already discussed this. The filter circuit is just to remove the ripples, or we want the unwanted ripples to be removed out from the discrete or the non-uniform AC waveform. So in this way, we are just removing the ripples. Now full wave rectifier, by using the first full wave rectifier, that is center tap bridge rectifier or center tap rectifier, in which the transformer, the secondary windings of the transformer are attached to the output load. In the middle of the secondary winding, we just attach a load resistance or the output load. And the working of center tap. Now, after discussing the center tap full wave rectifier, the characteristics of center tap full wave rectifier, first is the ripple factor, rectifier efficiency, peak inverse voltage, DC output current, DC output voltage, root mean square value of load current, that is IRMS, root mean square value of the output load voltage, that is VRMS, in the form factor. Now the advantages of full wave rectifier with center tap transformer, disadvantage of center tap transformer. Now center tap full wave rectifier with filter circuit. Now we just want to remove the ripples. And now we are going to start with bridge wave rectifier. The full wave rectifier category, another full wave rectifier category is the bridge wave rectifier. However, the center tap full wave rectifier has one drawback, that is center tap transformer used in it is very expensive and occupies large space. To cut this extra cost, scientists develop a new type of rectifier known as bridge rectifier. In bridge rectifier, center tap transformer is not required. If stepping down or stepping up of voltage is not required, then even the transformer can be eliminated in the bridge rectifier. So the rectifier efficiency of bridge rectifier is almost equal to the center tap full wave rectifier. The only advantage of bridge rectifier over center tap full wave rectifier is the reduction in cost. In bridge rectifier, instead of using the center tap transformer, 4 diodes are used. So this is the pictorial representation or diagrammatic representation of a bridge wave rectifier. And in this way, we are just doing the connection or contacts of the diodes to get the output across the load resistance in a full wave, that is through the negative half of the AC input and the positive half of the AC input. So the DC output is obtained without the fluctuation, and whatever the ripples are to be come out after the through the output, that can be further removed by the filter circuits. Okay. The 4 diodes D1, D2, D3, D4 are arranged in series with only 2 diodes allowing electric current during each half cycle. For example, As we had seen in the figure, diode D1 and D3 are considered as one pair, which allows electric current. And during the positive half cycle, D1 and D3, D1 and D3, they are allowing the current in the positive half cycle. Okay, as you are observing the positive half cycle, this D1 gets on and the current passes through and comes to the point D. Then it finds the blockage through D4 and it moves to the RL and it is conducted through D3. D3 will be open in the forward bias and the cycle will complete. For the negative half cycle, again the load, the negative half cycle just come, then this B point will become the positive point and A will become the negative terminal. So the D4 will start conducting and the current passes through the D4, then RL and then D2 and the cycle get completes. So during the both positive and negative half cycles, the diodes alternatively conducting and results in an output DC current. So during the positive half cycle, diode D2 and D4 are considered as another pair which allows electric current during the negative half cycle of the input AC signal. So this is a diagrammatic representation of conduction of diodes through the positive half cycle and through the negative half cycle. In both the arrangement, you see that the load resistance or the load which is connected gets the current in the very same direction. Okay. So the arrangement need to be keep in mind that how you are going to arrange the diodes. Thus, a bridge rectifier allows electric current during both positive and negative half cycle of the input AC signal. As the AC input is going in a first wave, then D1 and D3 are going to conduct and give the output as shown. And for the next negative half cycle, D2 and D4 conduct, and these two output get add up, and the total output current is shown in the last waveform, and it is again fluctuating DC, not the constant DC. So advantages of bridge rectifier: low ripples in the output DC signal. The DC output signal of the bridge rectifier is smoother than the half wave rectifier. In other words, the bridge rectifier has fewer ripples as compared to the half wave rectifier. However, the ripple factor of the bridge rectifier is same as the center tap full wave rectifier. High rectifier efficiency. The rectifier efficiency of the bridge rectifier is very high as compared to the half wave rectifier. However, the rectifier efficiency of the bridge rectifier and center tap full wave rectifier is same. Low power loss. In half wave rectifier, only one half cycle of the input AC signal is allowed and the remaining half cycle of the input AC signal is blocked. As a result, nearly half of the applied input power is wasted. However, in the bridge rectifier, the electric current is allowed during both positive and negative half cycles of the input AC signal. So the output DC power is almost equal to the input AC power. Disadvantages of the bridge rectifier. So bridge rectifier circuit looks very complex. In a half wave rectifier, only a single diode is used, where as in center tap full wave rectifier, 2 diodes are used, but in the bridge rectifier, we use 4 diodes for the circuit operation. So the bridge rectifier circuit looks more complex than the half wave rectifier and center tap full wave rectifier. More power loss as compared to the center tap full wave rectifier. In electronic circuits, the more diodes we use, the more voltage drop will occur. The power loss in bridge rectifier is almost equal to the center tap full wave rectifier. However, in bridge rectifier, the voltage drop is slightly high as compared to the center tap full wave rectifier. This is due to 2 additional diodes, that is total 4 diodes, In center tap full wave rectifier, only one diode conducts during each half cycle. So the voltage drop in the circuit is 0.7 volt, but in the bridge rectifier, two diodes which are connected in series conduct during each half cycle. So the voltage drop across occurs due to the two diodes, which is equal to 1.4 volt. However, the power loss due to this voltage drop is very small. Now, the questions or the quiz related to the topics which we had covered, which of the following is not a type of rectifier? Precision half wave rectifier, bridge rectifier, peak rectifier. So they all are rectifiers. So none of the above mentioned is not a type of rectifier. All are the type of rectifier. Second, for a half wave or full wave rectifier, the peak inverse voltage of the rectifier is always greater than input voltage, smaller than input voltage, equal to the voltage, greater than input voltage for full wave rectifier is smaller for the half wave rectifier. The solution is the B option is the right answer, the smaller than the input voltage. For half wave rectifier having diode voltage Vd and supply input of V1, the diode conducts for pi minus 2 phi, where phi is given by. So when we had just uh, go through the solution of the theory, we just find out that the option C is uh, right answer, sine inverse Vd by V1. So phi is inverse, sine phi is equals to Vd by V1. So phi is equals to sine inverse Vd by V1. Bridge rectifier is an alternative for full wave rectifier, peak rectifier, half wave rectifier. None of the above. It is a alternative for full wave rectifier. Which of the following is true for bridge rectifier? The peak inverse voltage or PIV for the bridge rectifier is lower when compared to an identical center tap rectifier. The output voltage for the center tap rectifier is lower than the identical bridge rectifier. C option, a transistor of higher number of coil is required for center tap rectifier than the identical bridge rectifier. So which of the following is true for bridge rectifier? All of the above mentioned is true for the bridge rectifier. So option D is right answer. The diode rectifier works well enough if the supply voltage is much greater than 0.7 volt for a smaller voltage of few hundreds of millivolt input. Which of the following can be used? Super diode, peak rectifier, precision rectifier, none of the mentioned. So option A is right answer, is super diode. Which of the following is not true for Schottky barrier diode? It is formed by bringing metal into contact with moderately doped N-type semiconductor material. In the Schottky barrier diode, current is conducted by mainly by minority carriers. The C option, the forward voltage drop of conducting Schottky barrier diode is lower than that of a PN junction diode. And the fourth option, SBD are used in the design uh, of a special form of bipolar transistor logic circuit. So which of the following is not true for Schottky barrier diode? The Schottky barrier diode is not designed for special form of bipolar transistor logic circuit. Basically, it is used for high switching circuits. So option D is not true for Schottky barrier diode. The photodiodes are part of optoelectronics. B. High intensity discharge. C. Low pressure discharge. D. None of the above mentioned. So photodiodes are part of optoelectronics. So option A is the right answer. 9. Which of the following is true for LEDs? The light emitted by LED is inversely proportional to the current flowing through the diode. LED operate in a manner opposite to the working of the optoelectronics or photodiodes. LED cannot be used to generate coherent source of light. None of the above mentioned. So option B is correct. LED operate in manner opposite to the working of optoelectronic or photodiode. So this is all about the rectifiers. Thank you. Now we are going to start with transistor, bipolar junction transistor. So just wait a minute. I'm changing the slide. So now we are going to start with transistors or bipolar junction transistor BJT. So bipolar junction transistor is a three-terminal device, or transistor is a three-terminal device. Basically, the transistors are formed by the help of three types of semiconductors, either PNP or NPN. That is, one semiconductor is sandwiched between the other two same semiconductors, and the resultant element form is known as bipolar junction transistor. Now, the diagrammatic representation. Bipolar junction transistor, like a PN junction diode, a transistor is also made up of combination of p-type and n-type semiconductor layers. However, unlike the PN junction diode, the transistor contains either one p-type and two n-type semiconductor layers, or one n-type and two p-type semiconductor layers. The transistor that is made up of one p-type and two n-type semiconductor layers is known as NPN transistor, whereas transistor that is made up of n-type and two p-type semiconductor layers is known as PNP transistor. So the definitions are like this. A transistor is a three-terminal semiconductor device that amplifies or switches the flow of current. So basically, the amplifiers are having the basic component, or the basic element for the amplifiers are the BJT. So bipolar junction transistors are the basic element for the amplifiers, or some of the time it can also be used for the switching, or switching the flow of current. Or a transistor is an electronic device that controls the current flow or switches the current flow. A transistor is an electronic device that controls the movement of electrons, that is charge carriers. Or a transistor is a small electronic device that controls the flow of electric current. So basically, we are controlling the flow of current by the means of BJT. So this is the diagrammatic representation of PNP or NPN type transistor, and the nomenclature is like this. The one terminal is known as emitter, second middle one is known as base, and the third one is known as the collector, emitter base collector for NPN type, or for PNP type, emitter base collector, as shown in the figure. The difference between the two symbol is just by the arrowhead. In NPN transistor, one arrowhead is moving out from base to emitter side, and in PNP transistor, one arrowhead moving inside from emitter to base. So on the basis of arrowhead, and these arrowheads are nothing but they are showing the moving of electrons from the majority side to the, or crossing of or movement of the electrons. Okay, so we will see how this arrowhead comes out, but for future reference, you just kept in mind that the arrowhead should designate to differentiate between the NPN and PNP type transistor. So this is the symbolic representation of two types of transistor, and this is the also a symbolic representation of two types of transistor. Now, brief history of transistor. The transistor was successfully demonstrated on December 23, 1947 at Bell Laboratories, New Jersey. The three individuals credited with the invention of the transistor were John Bardeen, William Shockley, and Walter Brattain. Among these three individuals, William Shockley played a key role in the invention of the transistor. What is transistor? A transistor is a three-terminal semiconductor device that amplifies electronic signals such as radio and television signal. Before the transistor came into existence, vacuum tubes are used to amplify the electronic signals. But nowadays, vacuum tubes are replaced by transistors because of its various advantages over vacuum tubes. The various advantages and disadvantages of transistors are and vacuum tubes are as follows. Advantages of vacuum tubes: vacuum tubes can be easily replaced, uh, tolerant of large overload and voltage spikes, superior sound quality. Disadvantages of vacuum tubes: high power consumption, having high cost. Vacuum tubes are very bulky, so they occupy more space, and high voltage is needed to operate the vacuum tubes, and they produce large heat and having lower efficiency. Now, advantages of transistor: they are of low power consumption, they are having low cost, small in size, they have higher efficiency, low voltage is needed to operate the transistor, high physical rigidness than vacuum tubes, produce far less heat than vacuum tubes, and transistors are lighter than vacuum tubes. That means they are not bulky, they require very less space because they are in very small size. The disadvantages of transistors: less tolerant of overloads and voltage spikes than vacuum tubes. Maintenance is very difficult. Uh, it is difficult to replace the transistors. Now, this is the classification chart of the transistor. It's a very clear and broad classification of the transistor, which can be betterly understood by the tree diagram. A transistor is classified among two categories. One is BJT and second one is FET. The one BJT stands for bipolar junction transistor and FET stands for field effect transistors. The BJT are the normal transistors, which is underly categorized in the two categories. One is NPN and second one is the PNP. Whereas FET is categorized further in two categories. One is JFET and second is MOSFET. So junction field effect transistor and metal oxide semiconductor field effect transistor. Now, junction field effect transistor, that is JFET, is further on the different mode they are going to run out, that is depletion mode and the enhancement mode. So MOSFETs are on the two bases of mode of operation. One is the depletion and second is enhancement. So JFET is only on the basis of depletion and is further categorized into N type N channel JFET and P channel JFET. Whereas MOSFET uh, is under depletion and enhancement type. So under depletion, it is N channel depletion type MOSFET and P channel depletion type MOSFET. Whereas in so This is the classification of transistor, and now we are going to study the each classification in details. So the transistors are mainly classified into two types: bipolar junction transistor (BJT) and field effect transistor (FET). In a bipolar junction transistor, both free electrons and holes conduct electric current, whereas in field effect transistor, either free electrons or holes conduct electric current. The bipolar junction transistors are again classified into two types. They are NPN and PNP type transistors. The field effect transistors FET are classified into two types: JFET and MOSFET. Just wait a minute. The field effect transistors are classified into two types: JFET and MOSFET. JFET stands for junction field effect transistor, and MOSFET stands for metal oxide semiconductor field effect transistor. Uh, uh, the junction JFETs and the junction field effect transistor JFETs in depletion modes are classified into two types: N channel and P channel. The MOSFET transistors classified into two types: depletion mode MOSFET and enhancement mode MOSFET. The depletion mode MOSFET is classified into two types: N channel and P channel. The enhancement mode MOSFET is classified into two types: N channel and P channel. Next, a bipolar junction transistor or BJT uh, is a three-terminal electronic device that amplifies the flow of current. It is a current control device. In bipolar junction transistor, electric current is conducted by both free electrons and holes. Unlike a normal PN junction diode, the transistor has two PN junction types of bipolar junction transistors. The bipolar junction transistors are formed by sandwiching either N-type or P-type semiconductor layer between pairs of opposite polarity semiconductor layers. Bipolar junction transistors are classified into two types based on their construction. They are NPN transistor and PNP transistor. Terminals of BJT emitter, as name suggests, the emitter section supplies a charge carriers. The emitter section is heavily doped so that it can inject a large number of charge carriers into the base. The size of the emitter is always than that base. Base, the middle layer is called base. The base of the transistor is very thin as compared to emitter and collector. It is very lightly doped. Collector. The function of the collector is to collect charge carriers. It is moderately doped. That is, the doping level of the collector section is in between emitter and base. The size of the collector is always greater than emitter and base. The collector area in the transistor is considerably larger than the emitter area. This is because the collector region has to handle more power than the emitter does, and more surface area is required for heat dissipation. The various applications of bipolar junction transistors include television, mobile phones, computers, radio transmitters, audio amplifiers. BJT operation mode, basically BJT or the transistor operate in four different modes. One is the active mode, second is the cutoff mode, third is the saturation mode, and the fourth one is the inverted mode. In order to operate transistor in one of these regions, we have to supply DC voltage to the NPN or PNP transistor. Based on the polarity of the applied DC voltage, the transistor operates in any one of these regions. Applying DC voltage to transistor is nothing but the biasing of the transistor. Active mode. In the active mode, one junction, emitter to base, is forward bias, and another junction, collector to base, is reverse bias. In other words, we assume two PN junctions as two PN junction diodes. One diode will be forward bias and another diode will be reverse bias. The active mode of operation is used for the amplification of current. This is the diagrammatic representation for active mode for NPN transistor. We have to just keep the emitter base in forward bias and collector base in reverse bias. So this particular mode of biasing is known as active mode of biasing. And by doing this, when we are just going to get the output across the load is get amplified. Either the voltage will be amplified or whatever you want in the current amplification can be done to this mode or through this mode. Cutoff mode. In the cutoff mode, both the junctions of the transistor emitter to base and collector to base are reverse biased. In other words, we assume two PN junctions as two PN junction diodes. Both the diodes are reverse biased in cutoff mode. We know that in reverse bias condition, no current flows through the device. Hence, no current flows through the transistor. Therefore, the transistor is in off state and acts like an open switch. The cutoff mode of the transistor is used in switching operation for switch off applications. This is the diagrammatic representation for cutoff mode by saying that both the emitter base and collector base are reverse bias in the case of NPN transistor. Saturation mode. In saturation mode, both the junction of the transistor emitter to base and collector to base are forward bias. So, in other words, if you assume two PN junctions and as two PN junction diodes, both the diodes are forward bias in saturation mode. We know that in forward bias condition, current flows through the device, hence electric current flows through the transistor. In saturation mode, free electrons, charge carriers, flow from emitter to base as well from collector to base. As a result, a huge current will flow to the base of a transistor. Therefore, the transistor in saturation mode will be in on state and acts like a closed switch. The saturation mode of the transistor is used in the switching operation for switching on application. This is a diagrammatic representation for biasing for the saturation mode. That is, both the emitter base or collector to base junctions are forward bias in the case of NPN transistor. NPN transistor, when a single p-type semiconductor layer is sandwiched between two n-type semiconductor layers, an NPN transistor is formed. NPN transistor symbol, the circuit symbol and diode analogy of NPN transistor is shown in the figure. So this is the symbolic representation of NPN transistor, where the arrow head moving out from the base to the emitter side. Working of an NPN transistor, unbiased NPN transistor. When no voltage is applied to a transistor, it is said to be unbiased transistor. At the left side N region emitter and right side N region collector, free electrons are the majority carriers and holes are the minority carriers. Whereas in P region base, holes are the majority carriers and free electrons are in the minority carriers. So this is a diagrammatic representation. As you see, On the both the junction, the depletion region is formed. So this is the diagrammatic representation of NPN transistor, and in case of PNP, the majority carriers instead of the electrons, showing here as the majority carriers, holes will be the in the majority carriers. We know that the charge carriers, free electrons and holes always try to move from higher concentration region to the lower concentration region. For free electrons, N region is the higher concentration region and P region is the lower concentration region. Similarly, for holes, the P region is the higher concentration region and N region is the lower concentration region. Therefore, the free electrons at the left side N region emitter and right side N region collector experience a repulsive from each other. As a result, the free electrons at the left side and the right side N regions emitter and collector will move into the P region. During this process, the free electrons meet the holes in the P region base near the junction and fill them. As a result, depletion region, positive and negative ions, is formed at the emitter to base junction and base to collector junction. At the emitter to base junction, the depletion region is penetrated more towards the base side. Similarly, at the base to collector junction, the depletion region is penetrated more towards the base side. This is because at emitter to base junction, the emitter is heavily doped. The emitter is heavily doped and base is lightly doped. So the depletion region is penetrated more toward the base side and less towards the emitter side. Similarly, at the base to collector junction, the collector is heavily doped and base is lightly doped. So the depletion region is penetrated more towards the base side and less towards the collector side. The collector region is lightly doped and the emitter region than the emitter region. So the depletion layer width at the collector side is more than the depletion layer width at the emitter side. So when you had seen in the diagrammatic representation, the width of the depletion region towards the collector side is more than the depletion width towards the emitter side. Okay, that's why this is the reason, because the area is large. We are just kept the area of the emitter is large. Why depletion region penetrates more towards lightly doped side than the heavily doped side? We know that the doping is the process of adding impurities to the intrinsic semiconductor to improve its electrical conductivity. The electrical conductivity of the semiconductor depends on the doping level added to it. If the semiconductor material is heavily doped, its electrical conductivity is very high. That means the heavily doped semiconductor material has a large number of charge carriers which conduct electric current. If the semiconductor material is lightly doped, its electrical conductivity is very low. That means the lightly doped semiconductor material has a small number of charge carriers and holes are the minority charge carriers. In NPN transistor, the left side N region is heavily doped, so the emitter has a large number of free electrons. We know that in p-type semiconductor, holes are the majority charge carriers and free electrons are the minority charge carriers. The p region base is lightly doped, so the base has a small number of holes. The right side N region is moderately doped. Its doping level lies between the emitter and the base. Biased NPN transistor. When external voltage is applied to an NPN transistor, it is said to be a biased NPN transistor. Depending on the polarity of the applied voltage, the NPN transistor can be operated in three modes: active mode, cutoff mode, and saturation mode. The NPN transistor is often operated in active mode because in active mode, the NPN transistor uh, amplifies the electric current. So let's see how an NPN transistor works in active mode. Let us consider an NPN transistor shown in the figure below. Uh, in the figure below, the emitter base junction is forward biased by the DC voltage VEE, and the base collector junction is reverse biased by the DC voltage VCC. So this is the diagrammatic representation of NPN transistor in active mode. Emitter base junction is forward bias and the collector base junction is the reverse bias. So due to reverse biasing, we had already seen in the case of diodes, the depletion width get more wider. And in the case of forward bias, the depletion width is get a little bit smaller. So you find the difference between the depletion width between base emitter and base collector, and this is the internal reactions of the holes and the electrons which takes place during the biasing in the forward biasing in the emitter base junction, and the collector base junction is reverse biasing. So basically this will give the output as an amplified output. Due to the forward bias, large number of free electrons in the left side and region experience a repulsive force from the negative terminal of the DC battery, and also they experience an attractive force from the positive terminal of the battery. As a result, the free electrons start flowing from emitter to base. In the similar way, holes in base experience a repulsive force from the positive terminal of the battery, and also experience an attractive force from the negative terminal of the battery. As a result, the holes start flowing from base to emitter. Due to the applied external voltage, uh, each emitter atom has more than one or two free electrons. Hence, each emitter atom donates more than one or two free electrons to more positive ions. As a result, the positive ions become neutral. Similarly, each base atom accepts more number of electrons from more negative ions. As a result, the negative ions become neutral. We know that depletion region is nothing but the combination of positive ions and negative ions. Thus, the depletion width at the emitter base junction reduced by applying the forward bias voltage. We know that electric current means flow of charge carriers. The free electrons, negative charge carriers, flow from emitter to base, whereas the holes, positive charge carriers, flow from base to emitter. These charge carriers conduct electric current. However, the conventional current direction is same as the direction of holes. Thus, the electric current flows from base to emitter. Base collector junction. Due to the reverse bias, a large number of free electrons in the right side N region collector experience an attractive force from the positive terminal of the battery. Hence, the free electrons move away from the junction and flow towards the positive terminal of the battery. As a result, a large number of neutral collector atoms loses electrons and become positive ions. On the other hand, holes in the region base experience an attractive force from the negative terminal of the battery. Hence, the holes move away from the junction and flow towards the negative terminal of the battery. As a result, a large number of neutral atoms gains electrons and becomes negative ions. Thus, the width of a depletion region increases at the base collector junction. In other words, the number of positive and negative ions increases at the base collector junction. So, that is all for today's lecture. We will continue this lecture in the next class or in the next lecture. So, thank you. Thank you all.